So first, thank you for inviting me. I'm Kelsey Morgan. I'm a graduate student at the University of Wisconsin-Madison, and I'm going to tell you about our efforts to develop transition and edge sensor arrays for X-ray astronomy. So this project is primarily a collaboration between our group at UW-Madison and the X-ray microcalorimeter group at Goddard Space Flight Center. We've also got colleagues that we work with at MIT, Yale, and the University of Miami. There's a long, about 40 years of history of collaboration between the UW-Madison and NASA on X-ray sounding rocket missions. And so our goal is to develop a new technology to keep pushing that collaboration forward to continue on in the future. Our funding is primarily through various NASA channels. I myself am a Space Technology Research Fellow. That's been really great for facilitating my work with Goddard. The UW-Madison group is primarily funded through a series of APRA grants. And then, of course, the sounding rocket, NASA Sounding Rocket Program funds and manages the actual rocket flights. Transition edge sensors are superconducting single photon detectors, and in particular, they're thermal detectors. And what that means is that when an X-ray is absorbed in the detector, its energy is converted to heat, and what we actually measure is a change in temperature. And we use a thin superconducting film, and we run a very small current through it to keep it at a temperature that's just in that sort of transition region where it's about to transition from its normal resistive state into its superconducting state. And that transition isn't a step function. It happens over a very narrow range in temperature. And so in that narrow temperature range, the TES acts as a very sensitive thermometer. And we can exploit that effect to make a very precise measurement of the energy of incoming X-rays. And as we'll see later, TESs are not only very high resolution, but they can also be highly efficient. So they make really great X-ray spectrometers. I probably don't have to justify the use of X-ray spectroscopy to this crowd, but I'll just mention that being able to do high resolution X-ray spectrometry really enables us to study a lot of very interesting high energy phenomena. It's been a powerful probe of gas dynamics in the interstellar and intergalactic media, things like matter falling into black holes, supernova explosions. There's really all kinds of areas where X-rays give you information that you just really can't get at any other wavelength. And TESs have been around as X-ray detectors since about the late 90s, and they've made tremendous progress in the laboratory. So groups at Goddard Space Flight Center and NIST have demonstrated detectors with resolving powers of over 1,000, so a 1 to 1.5 EV resolution at 1.5 keV. And TESs have also been used successfully at longer wavelengths, so for example in the submillimeter, on ground-based telescopes and on balloons. Now, in this context, they're not single photon detectors anymore. Instead, they're measuring the average power of the incoming light. So we call that a bolometer as opposed to the single photon detector, which is a microcalorimeter. So as bolometers, they've been successfully deployed in a number of science instruments. So for example, the South Pole Telescope or SCUBA 2, which is the focal plane array is shown in the picture on the lower left there. So as single photon detectors, on the other hand, we're not quite as far along. TRL is about 4 to 5 in the lab, but they've never been used in space, so on a rocket or a satellite instrument. So what our group is trying to do is put together a TES array that could fly as a sounding rocket mission. And our science goal is to study the diffuse X-ray background. So this is something that was discovered in the 1960s with sounding rockets. And what we found is that, sort of to our surprise, the entire sky glows faintly and fairly uniformly in the soft X-ray. So that's in the sort of 50 to a couple thousand kiloelectron volt energy range. And initially, it was assumed that this was probably extragalactic, but as soon as we started studying this source in detail, we realized that a lot of it was probably actually produced within our own galaxy. So this image that I've got up here was made by the ROSAT satellite in the mid-1990s. And ROSAT didn't have great energy resolution, so the information is sort of divided into 3 very broad spectral bands. So at the highest energies, which is about 1 to 2.5 keV, which is blue in this image, the emission is fairly uniform across the entire sky, and that probably is mostly extragalactic. It's sort of a superposition of many very faint point-like sources. It's probably matter falling into supermassive black holes at the center of very distant active galaxies. Now, at the lower energies, which is shown in red and yellow in that image, the source is probably actually mostly coming from within our own Milky Way. And our current best models is that this is probably 1 to 2 million degree gas that's sort of distributed throughout the galaxy. It's probably the result of past supernova explosions, which get ejected and then over time sort of mixed into the interstellar medium. And by studying the X-ray spectrum of this emission, we think we can better understand where it's produced and how it sort of gets incorporated into the interstellar medium. So studying a sort of faint, diffuse source like this poses a pretty big experimental challenge. So the sort of current workhorse detectors in X-ray astronomy are CCDs and energy dispersive spectrometers. So for example, the instruments pictured here are the CCD camera and grating spectrometer that are aboard the Chandra X-ray satellite. And CCDs are great instruments for a lot of reasons. They're very efficient, they're fairly easy to use so far as X-ray detectors go, and they've been routinely incorporated into megapixel arrays. On the other hand, they're fairly low energy resolution. The best you can do with the CCD is maybe 20 to 50 times worse than what we think we can do with a microcalorimeter. And not only that, but CCDs have been developed to the point where they're actually starting to hit the sort of fundamental physics limit to the energy resolution. So there's not really a lot of room for future development so far as the energy resolution of these instruments goes. Now, on the other hand, you've got the grating or dispersive spectrometers. And these can be extremely high resolution, easily resolving powers of 1,000 or more. But that comes with the sacrifice of efficiency. So while a dispersive spectrometer is great for looking at a bright point-like object, they're not really good for faint objects. You can't really look at extended or diffuse emission with them. So we think that a TES can offer us kind of a best of both worlds, where you get that high resolving power, maybe up to 1,000, and you still have a high efficiency detector that can look at an extended object. So the constraints on our instrument are mostly going to come from the nature of the X-ray spectrum of the diffuse background and from the sounding rocket flight environment. Sounding rocket flights are very short. You typically get maybe 300 seconds of observing time, so you really need to get every photon. So we're going to target a 256 pixel array, and each pixel is going to need to be about 0.9 by 0.9 millimeters in surface area. The X-ray spectrum of the diffuse background is also very complex. It's made up of hundreds of very closely spaced emission lines. So at the bottom left there, I have plotted a simulation of a 1 million degree plasma with roughly solar elemental abundances. And then on the right, I've got sort of a zoomed in view of part of this spectrum, showing what it would look like if you point a real instrument at it. Now, if you were doing this with the CCD, in this energy regime, you might get sort of 40 to 50 EV, electron volt resolution, which means that spectrum on the right would just kind of look like one big blob. The best that we've done with microcalorimeters, space-based microcalorimeters in the past is about 8 EV, which is shown in the blue line at the bottom there. But to really get at the science, to really pick apart and understand this spectrum, we're going to need 2 EV or better energy resolution in this 250 EV regime. So that's our goal for this instrument. So the detector design itself starts with a bilayer transition edge sensor. We start with a thin film of an elemental superconductor. In this case, we're going to use molybdenum. And we add to that a layer of a normal metal. In this case, we're going to use gold. And by changing the relative thicknesses of those two layers, we can change the transition temperature of the film. So we can suppress the temperature from the bulk transition temperature of the molybdenum, which is about 800 millikelvin, down by an order of magnitude or more, so that we can operate these detectors at under 100 millikelvin. And that gives us a number of advantages. For one thing, it makes us more sensitive to what ends up being very small changes in temperature, and it also helps us to suppress the noise. So I've got a sort of cartoon drawing of what one of these detectors might look like on the left. There's the bilayer, to which we add superconducting leads to bring in the bias current. And then on top of the bilayer, we typically add a number of normal metal features, the banks and bars and stripes. This allows us to change the shape of the superconducting transition, and it also helps us to suppress noise. Typical scales for one of these objects, TESs might be 100 or so microns across. The thickness of the layers tend to be maybe 50 to 100 or so nanometers. So on the right, there's a photograph there of one of these detectors. You can see the superconducting leads coming in, and then the gold bilayer and added stripes, and that's covering up the molybdenum layer, which is underneath. So typically, TESs work best on pretty small scales. Now, I say small, but of course, I'm talking about devices that are a couple hundred microns, so they're still big compared to a typical CCD pixel. But unfortunately, we can't just scale that up and make a sort of square millimeter sized sensor. And so what we're going to do instead is we're going to attach a large, much larger piece of normal metal, and the job of that extra absorber is just going to be to capture the incoming X-rays and quickly and efficiently transport that heat into the sensor to be measured. So at the bottom right here, I've got a sort of cross-sectional drawing of how that might look. So we've got this large, thin piece of gold here, and it's coupled to the sensor right here. And I'm not drawing to scale here. This TES, like I said, might be 100 or so microns across, but this gap tends to be very small, only a micron or two, like you can see in the SEM image at the top right. And as I said before, typically these detectors are sort of a 100 to 200 micron scale. So people might make, most people make detectors that are about 100 microns across, coupled to an absorber that might be 200 or 300 microns. So for example, in the picture on the left, I'm showing you a top-down view onto one of these X-ray absorbers. And the T-shaped structure here and these 6 dots are mechanical supports that are holding the absorber up off of the substrate and also thermally connecting it to the sensor. Okay, so the challenge in making these large devices is primarily that the bigger the device, the larger the heat capacity. And since the energy resolution is going to get worse as the square root of the heat capacity, this quickly becomes a problem. So one solution to this problem is to simply make the gold layer absorber as thin as possible while still making it thick enough to sort of efficiently stop the incoming X-rays. So we're going to make the gold absorber about 200 nanometers thick. This poses a pretty significant fabrication challenge. I was curious the other day, so I did the arithmetic on this, and 0.9 millimeters by 200 nanometers is about the aspect ratio of a piece of paper. So we've got to make this really large, thin gold film. It's got to be self-supporting, and it has to. We also have to not sacrifice the good lateral thermal conductivity, so it has to quickly thermalize and transport that heat into the sensor. The other way we can combat the large heat capacity problem is we can try to engineer a more sensitive detector. So we can change the geometry of the TES to try and change the shape of that resistance versus temperature curve to make it steeper and give us more sensitivity. So this is a challenge on a couple of levels. It's a fabrication challenge, but it's also a detector design challenge. So we made the first devices in the summer of last year. And to start out with, we didn't try to make the 200 nanometer thick absorbers right away. We made them about 500 nanometers, and we knew that we would sacrifice energy resolution, but we wanted to start out with something that we thought had a pretty high chance of surviving fabrication. We also didn't quite hit our target for the bilayer transition temperature, so we wanted detectors that would operate at about 70 millikelvin. We got detectors that operated at about 100 millikelvin. So when you put those two things together, what we ended up with was a detector that got about 6 eV energy resolution at 1.5 keV. So that's not quite where we need to be, but on the other hand, the good news was that this matched very closely with what we would have expected based on modeling for devices like this. So we're pretty confident that scaling down to thinner absorbers and lower temperatures, we should see a pretty dramatic improvement over this number. And actually, our second round of fabrication just finished earlier this month. I was at Goddard last week testing the newest detectors while I was sort of preparing these slides to send out. And so I can tell you now that with our latest devices, we've roughly been able to cut this number in half. So that's good news, and we're pretty excited about testing more of those detectors and moving this project forward. So in thinking a little bit in the longer term, we've got to continue to refine our design a little bit. Once we get a detector that's performing at close to 2 eV, we can think about building a 256 pixel array. In the meantime, our colleagues at MIT are developing what's going to be the first or a sounding rocket payload to carry the first TES array, microcalorimeter array into space. That's the Micro-X project, and it's expected to launch hopefully late this year. They have a different science goal, so they're going to be imaging a supernova remnant, so their TES array is much smaller. But they've agreed to let us use their cryostat and their readout electronics after they've had their flight to fly our own array. And so we're hoping that in a few years we could have a flyable instrument. And sort of just to put this in the context of all the other X-ray missions that are going on right now, this is just sort of a rough timeline where I've sort of highlighted some of the relevant X-ray observatories. Right now we've got 3 really great instruments up in the sky: Chandra, XMEM Newton, and Suzaku. Those are CCD cameras, they're grading spectrometers, that's sort of the current generation. And these instruments are sort of their observing programs are sort of starting to wind down. And so now is sort of the time to start thinking about the next generation of instruments. One of those instruments is the Astro H project, expected to launch in the next year or so. That's going to carry a 36 pixel, I believe, microcalorimeter array. And that'll be really exciting. It's going to really improve on our current capabilities. And at about the same time, we should see the Micro-X flight. So we'll also get TES microcalorimeters in space for the first time. And then there's a bit of a gap, and the next sort of major X-ray observatory in the works is the Athena project. And Athena calls for a kilopixel array of transition edge sensors with sort of 2 EV type resolution. And so that really represents a significant step above what our current capabilities are. And so I think that there's kind of a gap here, both in time and in sort of what science we can do, where this project that we're working on fits in pretty nicely. Let's see if we can get, okay. So on the one hand, we think we can contribute to, significantly to TES technology development. On the other hand, we think we can also do a sort of unique science with this payload that you can't get from any of these satellite instruments that are currently available or will be available in the next 10 years or so. Sounding rocket launches tend to cost a few $1 million per launch. That's not cheap, but it's sort of orders of magnitude smaller than the budget for one of these satellite scale missions. They also have relatively shorter development times, and so you can test out new ideas, and you can really build more specialized scientific instruments to kind of target particular experiments that you can't do with a satellite instrument that has to be designed for sort of a broad, many user base. So we're as I said, currently testing prototype detectors. We expect to be flight ready maybe 2 to 3 years' time. And we're not going to stop at 2 eV, of course. We'd like to continue improving because as we can keep driving the resolution lower and lower, better and better, we can keep doing better and better science. And TESs are not only useful for astronomy. Like I said, they're going to be critical for developing next generation instruments like Athena, but they've also got many different ground-based applications as well. For example, in the last couple of years, there's been a really big push to develop instruments for ground-based terrestrial materials analysis. Things like alpha particle spectroscopy, X-ray emission and absorption spectroscopy. The group at NIST has been doing a lot of work on this and has deployed several instruments to synchrotrons around the country that are starting to do some pretty interesting science. So here's just some contact information. I would love to talk to any of you about TESs, about sounding rockets, X-ray spectroscopy. So here's my email, and also Dan McCammon, who is my graduate advisor and leader of this research group. He's up there as well. So I'll just leave you with sort of my 2 main points here. One, that TESs are a very promising technology for X-ray astronomy. They've got lots of other applications as well. And we think that this project can both help drive TES development for future X-ray astronomy, and also, in the meantime, do some unique science with the sounding rocket payload. I'd also just like to take a second to thank many important collaborators, especially the X-ray microcalorimeter group at Goddard Space Flight Center, also their detector design lab for actually making all of these devices, and the Space Technology Research Fellowship Program, which has really allowed me to spend a lot of time at Goddard doing the testing and detector development for this project. So with that, thank you. Any questions?
So for the absorbers, I saw you just were using, another way to lower the heat capacity would be to use a different material instead of gold. Have you thought about other absorber materials?
Yeah, so a lot of people like to use things like bismuth for X-ray absorbers. It's very high atomic number, so it makes a very efficient X-ray absorber, and it's very low heat capacity. The problem is that a lot of these sort of high Z, low heat capacity materials also tend to have poor lateral thermal conductivity. And what that means is that, in a big absorber, if you have an X-ray that hits in the far corner, it's going to take some finite amount of time for the heat to diffuse through the device and into the sensor. And of course, as you make these things bigger and bigger, that problem just becomes worse and worse. So the idea with using the gold is that you get pretty much the best lateral conductivity that you can get, and of course at the expense of heat capacity. So it's sort of a trade-off. I think that, the Micro X devices actually do use the bismuth. They are about half the surface area of what we've got, and they definitely do have position-dependent pulse shape on the sort of scales that would sort of kill our project. So that's sort of why we decided to go with the gold.